Okay, so now we're into the sublinear business, right? So the type of zero-knowledge proofs that are being zero-knowledge systems that are being used in the context of blockchain applications and other applications often have sublinear communication complexity. We already saw that even the MPC in the head approach can get there, but now we're interested in proof systems that have communication complexity that is typically, in practical terms, you can think of anywhere from 1,000 to 200,000 bits. In theory, think of it as being logarithmic, polylogarithmic, sometimes even constant number of group elements. Okay, this is the efficiency goal we're shooting for, and we'll see the type of information theoretic proof systems and cryptographic compiler that are geared towards this efficiency goal. Okay, so let's now get an overview of one of the exciting developments in the theory of computer science starting from the late 80s. This is the theory of interactive proofs that have led to this amazing notion of probabilistically checkable proof with low query complexity. Okay, so this traditional notion of PCP is a replacement for this. Okay, this is not yet the magical object. This is how we typically verify proofs or review papers, right? We're supposed to read it sequentially, check every step along the way, and complain if we find a bug. This is a sound process if we really do it or if a computer does it, but it's very tedious. And it's enough that a single bug is lurking in a place where we expect it the least to make the whole proof fail. Okay, this is why we don't like to review papers. The notion of probabilistically checkable proof makes verification much more efficient by making two changes to the classical model. First of all, allowing the verifier to toss coins, and second, settling for some small probability of soundness error. So this is really similar to the previous notion of PCP or zero-knowledge PCP that I mentioned. We can also require zero knowledge on top of the traditional notions of completeness and soundness. But the new part here is that we really require not only the number of queries made by the verifier to be small, but also the alphabet size to be small. Okay, so if you look at the type of zero-knowledge PCPs that you saw yesterday, based on MPC in the head approach, the verifier makes a small number of queries, but the symbols are very big. Here we want the PCP to be typically over a binary alphabet and the number of proofs to be small. For instance, we can require a soundness error of 1%, and the verifier making a constant number of queries to the proof. So the verifier actually reads only 100 bits of the proof, and yet it is convinced, except with 1% error probability, that the proof is correct. So these are the notions of completeness and soundness. Okay, you can amplify, right? If completeness is 1, soundness is 1/2, you repeat it, 7 or 8 times, sorry, and you get, I'm bad at powers of 2, so 9 times, how many? 9 times, sorry. You repeat it 9 times and the soundness error will become less than 1%. Okay. So this fantastic PCP theorem from the early 90s with the latest simplification by Dinur says that any statement that you can prove, so any statement in the complexity class NP, can be compiled, or the proof, the classical proof, can be compiled into this magical PCP form that can be verified very efficiently. The verifier reads only a constant number of bits if you want constant soundness error. You can make it zero knowledge generically with a small overhead. You can think of it as an information theoretic compiler from a PCP that has no zero knowledge to a PCP with zero knowledge, so such compilers exist. And this is fantastic, okay? Except for 2 problems. The first problem is that it's not clear how to use it. It's again the same type of problem I discussed before when I talked generically about these proof systems. So, as before, if we don't use the crypto compiler and just naively have the verifier ask the prover to give her the bits of the proof that she wants. This will fail to be sound because the prover can just give the verifier the bits that would make her happy, right? Knowing the soundness critically relies on independence. The proof has to be written down before the queries are picked. The proof cannot change dynamically based on the queries of the verifier. Okay, this is critical for the soundness, and this is why we need a crypto compiler. Okay, so this doesn't work. Instead, the traditional crypto compiler, the one that was first proposed to get sublinear communication argument, first by Kilian using standard collision-resistant hash functions, but requiring interaction, and then by Mikali applying the Fiat-Shamir heuristic and using a random oracle to make it non-interactive. So this compiler is based on this notion of a Merkle tree. A Merkle tree, also commonly used in blockchain. You've heard about it from Manoj, and I guess you'll hear about it again. It's just a way, a tree-based hashing of a long message. In this case, it's a proof. You just write the proof on the leaves of this hash tree, and you hash down and hash down and hash down until in the root you get a short commitment. In practical terms, this will be 256 bits. And now this type of commitment, we have easier ways of committing, right? We saw also easier ways of committing, but the special feature that is useful in this kind of commitment is that we can locally open any bit of the proof using a small amount of communication and while still respecting the binding property of the commitment. So if the verifier says to the prover, hey, please reveal pi 4, right? Which is what, say this is a query made by the PCP verifier. The PCP verifier wants to read the 4th bit. So in the compiled proof system, after the prover commits to the proof using this hash tree, the verifier says, please open bit number 4. And now you can think of these bits of the proofs as being grouped into blocks just to meet the syntax of this hash function, or you can pad them, right? But in any case, if the prover wants to reveal pi 4, then this is done by revealing not only the path from the root to this leaf, but also the siblings of the nodes on this path. Okay, so given these hash values and the siblings, the verifier checks that everything is consistent. So the hash of these two is equal to this value, the hash of these two is equal to this value, the hash of these two is equal to the root of the commitment. This is the only information that is actually given to the verifier as the commitment. If everything checks, then the verifier is convinced that the prover hasn't changed his mind, because you can show that if the prover can open a specific bit of the message or proof in 2 different ways, then the prover can find a collision in the hash function. So this can be based on any collision-resistant hash functions, which in turn can also be based on standard assumptions. In practice, we will typically use functions like heuristic functions like SHA-256. In theory, it can be based on standard assumptions. Okay, so taking a very high-level view at this approach, we start with this witness. We then do this PCP encoding, so we introduce a lot of redundancy. This is the PCP proof. And now we apply this cryptographic hashing followed by this opening of PCP queries by revealing path on this on the hash tree. Okay, so this is the process. And if you think about it for a second, there's something here that looks very wasteful or redundant. What is wasteful about this process? Okay, first of all, we have this very computationally heavy step of taking the witness. Not only do we expand it by a lot, so known PCP constructions have a big blow up in communication or in proof size, but also they're very computationally intensive. Okay, so we do this very expensive encoding of the proof, and then we kind of shrink it down, right? So why not just go directly? Why do we need this process of first working hard to expand the proof and then shrinking it down, right? So there is some redundancy. And in reality, these PCPs are super expensive. So they're implementable. There is some Eurocrypt paper that is actually implementing them, but for only very, very simple verification tasks. In general, they're super slow, these type of PCPs. And another problem is that even if you're happy, this part is only about computation because in the end you hash down everything to a short hash. So this hash is great, it's 256 bits, this is good. The bad part is that for every query made by the verifier, you have to open a path. So you can multiply 512 by log of the length of this PCP proof, and that's a lot. Okay, and moreover, in order to have good soundness, for this type of classical PCP, you cannot have a constant number of queries, you need to amplify to soundness by repetition. So in reality, the best case scenario will be, a couple of 100 bits that the verifier needs to read, and for each such bit, the concrete communication will involve like 512 times log of the size of the proof. So in practice, it will be, the thing that really kills us in practice for this approach is the computational complexity of this PCP encoding, right? This is not being communicated. This is just an intermediate state. So both computing time and space, this is still super expensive. We don't know it's inherently the case. I'm sure there will be a lot of progress, but at this point, we still do not have even semi-practical PCP constructions in this model. So I should say that this second disadvantage recently in two independent works by Lion Molavolta and by Bonnet, Bunz, and Fish, they propose using fancy public key crypto, namely hidden order groups, towards getting an asymptotically better version of this Merkle tree commitment. So using hidden order groups, you can commit to a vector and then open any subset of the bits that you want by communicating only a constant number of group elements. So this is asymptotically more appealing in a sense. However, this makes things even worse on the prover computation side. So this approach is still not practical, but at least it gives us some potential way of getting better succinctness than using this Merkle part of the compiler. So you can think of this as being two distinct compilers that work with the same information theoretic proof system. One uses a Merkle tree and only symmetric crypto. It's fast. This part is fast, right? The hashing is fast, but it's not very succinct because of the opening. And this type of compiler, it uses fancy public key crypto. It's more succinct, but it's computationally very slow. Okay? So even if we have a dream PCP encoding, which might exist in the future, still you can choose between succinctness and computation. And maybe these cryptographic compilers will be improved as well. Right, so we don't know, this is kind of an intriguing open question to understand really the limits of succinctness that we can get, say, in the random oracle model. That's a challenging theoretical question that is relevant also to practice. Yeah, so again, good thing about this overall construction, if you look at this Merkle tree instantiation, is that it only uses symmetric crypto. If you believe in the random oracle methodology, it gives us non-interactive proofs with no trusted setup and plausible post-quantum security. The downside is prover computation, the main downside. The secondary downside is suboptimal succinctness. Okay, so how do we get around the limitations? By relaxing the PCP model and adjusting the crypto compilers to these relaxed models. The first type of relaxation, it's something that's common in theoretical computer science, is to take whatever model you have and allow interaction. So the PCP model is non-interactive in the sense that there is a single proof written up in the sky and the verifier just accesses the proof in one shot. If you look at the interactive version of PCPs, that's only, surprisingly, it's only been recently considered, even though it's very natural. Here you have multiple rounds of proofs. So first the prover commits or writes this first proof pi1. The verifier can read a small number of bits from pi1. Then you have a random challenge coming from the verifier or out of the sky. It's a public challenge. And the prover has to respond to this challenge with a new proof that again the verifier may query, and so on and so on. So you can have another challenge and so on. And in fact, you can see that without loss of generality, the verifier can postpone all the verifications to the very end. So you can think of it as proof, random challenge, proof, random challenge, proof, random challenge. In the end, the verifier can read a small number of bits from each of these proofs. Okay, so the power of interaction is just the fact that, in a sense, the prover is on the hook, as is usual in the case of interactive proof. The prover is on the hook. The difference, on the hook, and then you have a random challenge. It's like an interactive investigation, which is very powerful. However, here too, it's just a generalization of the standard PCP model, so we obviously need a crypto compiler. Fortunately, the crypto compiler just follows in the same way as before. So you can use either the Merkle tree or the fancier compiler using a public key crypto to apply to this interactive version as well. And you can apply still the Fiat-Shamir heuristic. You have to be a bit more careful about the Fiat-Shamir heuristic when this interactive PCP has a super constant number of rounds, but this is a technicality, and in reality, this is not a problem, and people can now also prove that this works. So this notion of interactive PCP was first introduced in a work by Kalai and Raz, where they only considered a more restricted setting where you have a single PCP proof and then general interaction as in standard interactive proof. So in standard interactive proofs, the prover can send messages to the verifier, and the verifier reads all the messages that are sent from the prover. Here, the model is such that even subsequent messages can only be locally accessed by the verifier. So this is known as IOP, and it was introduced independently by Ben-Sasson, Chiesa, and Spooner, and by Rangan and Rothblum. And in fact, when you relax the classical PCP model to allow this interaction, this IOP model, it turns out that it is much easier to design efficient proof systems in this model. Okay, so there are certain goals that we do not know, for instance, how to get PCPs that blow up the circuit size by a constant factor without making a huge number of queries. In this model, we can do it, and the protocols are practical. And systems such as Stark and Aurora are based on such IOPs. Because you can use this Merkle tree-based compiler, these systems are transparent. They do not require trusted setup. They're plausibly post-quantum, and they only require symmetric crypto or hash function. So there's a trade-off between efficiency and rounds, but typically people use logarithmically. Typically the sweet spot is that the number of rounds is logarithmic, and yeah, this gives rise to simpler. IOPs are both easier to construct than classical PCPs and have attractive efficiency features. No, not at all. Even with constant soundness, yeah, it's not. Parallel repetition is not an issue in the PCP model. You can just repeat in parallel and soundness amplifies. It's really about interaction, allowing you to use different techniques. Okay, the second type of relaxation. So this relaxation, again, we took the classical PCP model and we just added interaction. An orthogonal relaxation of the classical PCP model is to use a richer type of queries. So recall that in a classical PCP, the verifier can make point queries. Namely, it can pick a set of symbols that it reads and it learns nothing about the other symbols. A more expressive type of queries are queries that compute linear functions of the proof. So you can consider each query as taking an inner, so now syntactically the proof is not a bit string or a string over an arbitrary alphabet, but now consider the proof as a vector over a finite field f, which will typically be large. Okay, typically the soundness of the proof system will be related to the underlying field. And now each query by the verifier is just a vector of the same length, where the verifier learns the answers, which are the inner product of the same pi with each query. Okay, so this is the 3-query linear PCP. Based on the answers and the statement, the verifier decides whether to accept or reject. Okay, so this model is implicit in the PCP context in the work of Aurora et al., but it was first introduced in the context of efficient argument systems in a joint work with Kushilevitz and Ostrovsky, and later abstracted in a work with Bitansky, Kieser, Ostrovsky, and Panes. So this is kind of just a template, a basic template for this linear PCP model, and there are also some different variations. But let me describe two things now. First of all, what do we gain from using this other model of linear PCP? And second is, how do we compile it? What is the cryptographic compiler? Let me start by addressing the first question. What are the advantages of linear PCPs over traditional PCPs? Okay, so we have more powerful set of queries. What do we gain from this? The first advantage is simplicity. So in the next slide, you'll see a self-contained, right? So I could not present here the proof of the PCP theorem, but I can present to you a proof of the linear PCP theorem, that every NP language has a linear PCP with a constant number of queries. This is surprisingly simple, and this simplicity is also, of course, correlated with concrete efficiency. Okay, beyond simplicity, such proofs, such PCPs, linear PCPs have better parameters. So they can be short. For instance, you can have the proof length easily, again, as in the interactive, here it's even easier in a sense to get linear PCPs where the proof length is just a constant times the circuit size. Okay, this is quite easy in the linear PCP model, not super easy. I'll show the simplest version I will show will have quadratic blow-up, but this is actually a breakthrough in this area of interactive proof systems and non-interactive proof systems, is this construction of linear PCPs via this notion of quadratic span program or quadratic arithmetic program that Chaya will talk about tomorrow. This is the work of Gentry, Gennaro, Gentry, Parno, and Reikova that kind of laid the grounds for practical zero-knowledge snarks that are based on linear PCPs. In terms of efficiency, here we can get, if the field is big, we can make a constant number of queries and the soundness error will be negligible. It will be 1 over field size, and the field size, you can make it negligible by just picking, in practice, you can make it good enough by working with a field that has, say, at least 80-bit elements. So in the PCP model, it's not just in the classical PCP model, and even in the IOP model, the interactive version, we inherently cannot get negligible soundness if we make a constant number of queries, because the prover can guess. A constant number of queries, there is only polynomially many options for picking them, so the prover can just guess them and violate soundness if the guess is right. Okay, so this is really an inherent advantage of linear PCPs. And by the way, even if you use classical PCPs or IOPs over big alphabet, this guessing attack still applies. So it's not that we're cheating by increasing the alphabet size, it's really the fact that we can make linear queries, they have more effective entropy than point queries. And this is, again, something that is very crucial in achieving succinctness. We have other useful properties that are relevant in some settings, such as reusable soundness. So in PCP, if you're in a setting where the verifier's queries are fixed, and now the prover can make many different proofs using the same verifier queries, the prover can gradually learn information via selective failure attacks. So the prover can take a valid PCP, and now replace one symbol by junk and see if the verifier is unhappy, then it means that this is one of the symbols that the verifier watches. So classical PCPs inherently do not have this reusable soundness feature, whereas linear PCPs can have it. In terms of succinctness, we can really get close to the theoretical limit. So, and in fact, Unlike classical PCPs, for classical PCPs, 3 queries are the minimum over binary alphabet. You can make 2 queries if you use a bigger alphabet, but still you cannot have a classical PCP with a single query, just again for the reason that I said before, you cannot achieve any, even if you want a soundness error 1/3, you cannot get it with a single query for general languages. You can, in fact, this is again something from the work with Bitansky et al. You can compile classical PCPs into linear PCPs that have a single query. Just some way of packing the answers of the PCP. You need to be careful to ensure soundness, but in principle, you can pack linear PCP queries. Okay, so let me show you how these PCPs work. This is a construction that was first introduced by Aurora et al. And then was applied towards sublinear proof systems or arguments in a work with Kushilevitz and Ostrovsky. And this is the so-called Hadamard PCP. So our goal is to design a linear PCP for the satisfiability of arithmetic circuits. So here there is a common input, which is this arithmetic circuit. And the prover wants to convince the verifier that it knows values. Think of it as operating over some big finite field. And the prover wants to convince the verifier that it knows x1 and x2 that would make the circuit output 0. Okay, of course we can express any, so this is, seems suitable to an arithmetic setting, but even if you have a Boolean circuit, you can still write it in this form. You need to ensure that a malicious prover will not feed the inputs with values that are not 0 or 1, but this can be easily done by just adding some check, an additional check. I will mention this soon. Okay, so how do we build a linear PCP for arithmetic circuit satisfiability? The first step is to write the verification as a satisfiability of a system of equations over the wires. So the prover and the verifier agree on some labeling of the wires and assign an input variable Wi for each wire I. Okay, so in this circuit we have 6 distinct wires. Note that fan out you only need a single W2 because we know that these 3 values should be the same. The second step is to write down what the verifier wants to check. So the prover should have in mind, right, the prover knows an input that makes the circuit evaluate to 0, so the prover can compute all these W's. But now the verifier wants to write the conditions on the W's that would make him happy. So first, for the circuit to be satisfied here, the convention is that the output is 0, so the verifier writes an equation and the prover, the W6 is equal to 0. The second type of requirements is consistency of the output of each gate with the inputs. So W6 should be the sum of W2, W4, and W5. So we write an equation W6 minus this sum equals 0. This multiplication gate corresponds to the equation the W4 minus W1 times W2 equals 0. Okay, and finally we have this constant. Here we don't have a requirement on W1, W2 because this the prover can choose arbitrarily. But now we want W3 to be 2, so we write W3 equals 2. So notice that all these equations, because we work over gates of fan-in 2, multiplication gates of fan-in 2, all of these are quadratic equations at most, right? You can have linear and quadratic. This will turn out to be crucial. But you can bring, even if you have a circuit with bigger fan-in, you can bring it into this form. So this is without loss of generality. Good. So now we just translated the problem of arithmetic circuit satisfiability to the problem of satisfying a system of quadratic equations. This is equivalent, right? If the prover can satisfy this system, it can find a satisfying assignment for the circuit and vice versa. Just again, a technicality, if we have a Boolean circuit, we can still write it as an arithmetic circuit, and then we need to add a requirement saying that x1 times 1 minus x1 is 0, and this ensures that x1 is either 0 or 1. We don't want the prover to cheat by using non-binary values. It's a standard trick that is also used a lot for MPC. Okay, so now I'm describing the actual, so once we converted the problem into a convenient form, namely satisfying a system of quadratic equations, I'm now spelling out the proof. The proof is extremely simple. This is the proof pi. First you write down the wires, so this is 6 field elements, and now you write the tensor of this vector with itself. So this is just a shortcut for the vector that consists of all products of Wi and Wj. So this is 6 plus 36. So overall, I mean, okay, this is wasteful. Of course, you can just use 6, choose 2, but you know, if you do it naively, this is 42 field elements are enough for this proof. Okay, asymptotically, it's quadratic in the circuit size. This is not so good, but still, it's feasible. And now the question is, how does the verifier check that indeed this is consistent with a satisfying assignment by only making a constant number of linear queries? Okay, so you have two types of checks that the verifier should make. First of all, it should be convinced that the second part is consistent with the first in the sense that indeed this contains the values Wi times Wj that are written in the first part of the proof. So for this consistency check, we can use two linear queries. The first linear query takes an inner product of W with a random vector R. Okay, and now we square it. And if we square it, it's just computing the same thing in two different ways. So I want to check the inner product of WR squared, that it's the same as we can now write it down as a degree 2 polynomial that has monomials of the form, you know, Wi times Wj multiplied by, okay, so if you write down, if you square a linear combination of the form sigma Wi Ri, what you get is precisely a linear combination of the Wi Wj whose coefficients are Ri times Rj. And this is exactly this inner product that is written here. The crucial point is that you can read this inner product by making a single linear query to the second part. So to sum it up, to check consistency of the second part with the first part, I take a random linear combination of the first part, I square it, and I check that this is equal to the corresponding linear combination of the second part. And you can easily prove using Schwartz-Zippel lemma that the probability that if there is an inconsistency, even in a single place, this test will fail except with 2 over field size probability, where 2 is the degree of the polynomial. The second test should check, so now that we're convinced that the second part is indeed consistent with the first, now it's easy to check that all these equalities hold. We again use a kind of a simpler version of Schwartz-Zippel where we just take a random linear equation, random linear combination of these equations. So we again pick some random R, and we apply the same linear combination R to the left-hand side and to the right-hand side, and we check that they're the same. So applying a linear combination to the right-hand side we can do on our own. We don't need to read anything. And here the key point is that because the left-hand side, these are all quadratic polynomials in W, also when we apply a linear combination to them, we get a bigger, a more complicated, but still a quadratic polynomial, and we can compute any quadratic polynomial in the W variables by taking a single linear combination of the W variables and all of the Wi Wj, right? Because quadratic polynomial is just a linear combination of Wi and Wi Wj. Okay, so if you combine the two checks, we get a linear PCP for circuit satisfiability, or which gives us linear PCPs for NP, using 3 queries with 2 over field size soundness error, right? So this is really, you know, orders of magnitude simpler than the corresponding feasibility result for classical PCPs. Good. So I should say that there is also other flavors of linear PCPs. For instance, here we assume that also a malicious verifier is kind of bound, committed to a vector and you can consider a more difficult model where the malicious verifier can apply an arbitrary function to the verifier's queries, which is motivated by some applications. But for the purpose of snarks, under strong assumptions, this version is good enough. That's a great question, and not as far as I know. So we thought about it a little bit. There might be some contrived problems. I mean, every PCP, yes. You can think of it as roughly corresponding to the hardness of a max lin, right, of satisfying a big number of linear equations, but this is not quite. You need some extra properties for this hardness to hold. But yeah, in principle, you could imagine a restricted type of linear PCPs as corresponding to interesting hardness of approximation result, but these types of linear PCPs are much harder to construct. Okay, so now, and again, I mentioned this is not something to be tried at home because of the quadratic overhead, even though there was a first wave of practical proof systems by Mike Wolfish and others that actually designed some optimized versions of Hadamard PCP for things like proving matrix computation. So you can design, you can apply in certain settings essentially the same technique as Hadamard PCP to get efficient proof systems, but generally the quadratic blowup is prohibitive, and this QAP-based constructions of Gennaro et al. That you'll hear a little bit more about tomorrow get around it and get the proof size to be linear in the circuit size instead of quadratic. Okay, this is relevant to the prover computation, not to succinctness. In terms of succinctness, you can get everything you want and more using Hadamard PCPs. But quadratic blowup in computation is typically prohibitive. Okay, so how do we compile these linear PCPs into actual proof systems? So the first generation, again, originating from IKO, and these are some work with growth, and this is Seti et al. This is an applied work that used these compilers. They use standard cryptographic assumptions, but also allow interaction. And the high-level idea, it's similar to the Merkle, right? So in Merkle tree, you design a commitment scheme that has a special decommitment functionality that it allows the prover to efficiently decommit to specific bits in the proof. Here you want a commitment scheme that supports linear queries, that allows the verifier to ask the prover, hey, give me this linear combination of the commitment vectors. So we still want the commitment vector to be succinct, but we want the prover to be able to open also succinctly any linear combination of the committed entries. So again, this was initially based on standard assumptions with some caveats. So the communication was only short in one direction and you had to balance things. So it had some caveats, but you could base it on standard assumptions and get certain kinds of sublinear communication arguments. Actually, you can get sublinear communication arguments for NP in the standard model under standard assumptions, but they are interactive. Nowadays, people call this primitive functional commitment. It's a commitment scheme that allows you to open a function of the information you committed to. The second generation, again, starting from really kind of a breakthrough work of growth from AsiaCrypt 10, and then Lipma and Gennaro et al. And Bitansky et al. Here the goal is to get non-interactive succinct arguments known as snarks, arguments of knowledge. And we have some barriers, Gentry Weeks tell us that we are unlikely to base them in a black box way on standard assumptions. But if we make strong assumptions, we can get such a compiler. So the type of assumptions we make are known sometimes as knowledge assumptions or targeted malleability. And essentially, you can think of them as something similar to the notion of homomorphic encryption that Manoj described, not fully homomorphic encryption, but standard homomorphic encryption that allows you to take an encrypted vector and compute any publicly known linear combination of this vector, right? So you can combine encryption of encryption of x1, x2, and x3 into an encryption of 5 times x1 plus 3 times x2 plus 7 times x3 without knowing x1, x2, x3, and this resulting encryption will be succinct. But you need the extra property that all you can do is these linear combinations. So it's kind of like homomorphic encryption scheme that doesn't have more homomorphism than we bargained for, that can only allow us to compute linear functions. It's a strong assumption. Again, you can instantiate it from so-called knowledge assumptions, knowledge in the exponent, originally by Damgard. But they're quite plausible, and they hold unconditionally in the generic group model. So if you model a group as a random object with random labels, then these assumptions probably hold in this generic model. For real-world encryption schemes, we can only conjecture them to satisfy this property. And if you have such an encryption scheme, I will describe it later, but for now, let me just tell you the high-level features. So, given these assumptions, we can get a compiler that takes any linear PCP and makes it into a non-interactive argument system, but the price we pay is that we need a long and structured common reference string. Right? Nowadays, people call it an SRS, structured reference string. The downsides of this, other than just having to load to your phone or whatever, or this huge string, is that there is an issue of trust, and I guess we'll hear a lot about it tomorrow. So you need to trust the entity that generated this string, because if this entity is malicious, it can violate soundness. So the soundness of these proof systems of the compiler relies on this reference string being honestly generated. You can make these proof systems publicly verifiable via pairing, so we'll explain the idea soon. And the high-level idea is to let this reference string include the encrypted queries. So the verifier, instead of telling, right, if the verifier tells the prover, hey, these are my queries, then soundness is gone. Instead, the verifier will encrypt the queries, and let's see how it works. Okay, so let's do it in stages, starting with the most naive attempt. So assume that you have this linear-only encryption scheme. Again, it's an encryption scheme that allows you to compute linear functions on the encrypted inputs and only linear functions. So what the verifier will do is we'll use this encryption scheme and generate this. This is a reusable common reference string. It's long, but it's reusable, so you can set it up once. Think of the verifier as doing it, and lock it inside this linear-only encryption scheme. Okay, so now every field element of the verifier's queries is encrypted. Now, and the verifier keeps the decryption key. Only the verifier knows how to decrypt. Now here comes the prover. He generates a proof and computes the encrypted answers, right? You can take an inner product of a vector that is known to the prover with an encrypted vector where the encryption was done by the verifier. This is the property of the linear-only encryption. And we also know that the prover can only apply this linear combination to each query. So does this work, or something here is still problematic? Okay, so now the verifier decrypts the answers and applies the decision procedure of the linear PCP. Does this work, or there is some subtle issue here? Exactly. So nothing here forces the prover to apply the same, to take the inner product of the same proof pi with each query. So the prover, a malicious prover, can definitely take different inner products, Q1 with pi 1, Q2 with pi 2, Q3 with pi 3. So for those who know the PCP literature, there's an alternative model called the multi-prover interactive proofs, which corresponds to these cheating strategies, but in this model, soundness is lost, right? So if you compile a linear PCP in this way, it will not necessarily be sound. Okay, so this is, okay, so again, so this is a bit going more slowly. So the first problem, again, is that if you use just a standard linear homomorphic encryption, the prover can compute more than just linear functions. We assume it away by just assuming that the encryption scheme is linear only. A bit about this linear only assumption. You can view it as an instance of a more general notion of targeted malleability, so it allows you to mull ciphertext, but in a targeted way, in a specific way. And compared to other types of assumptions or knowledge assumptions, one could potentially argue that it's nicer in the sense that if standard public key encryption schemes, say the Goldwasser-Mikhaeli scheme that Manoj mentioned, fails to have this property, it somehow says that we have some surprising functionality. So we can compute more than linear function on these Goldwasser-Mikhaeli ciphertext, which intuitively is surprising and can also lead to useful consequences. So in a sense, assuming that standard homomorphic encryption schemes that were not designed to be fully homomorphic, but only additively homomorphic, assuming that they satisfy this linear-only property is a plausible assumption, including for post-quantum encryption schemes based on lattices. And as I said, this has a win-win flavor in the sense that if this assumption fails, then we believe there is certain leap of faith, but we believe that this will fail in an interesting way that will be useful. The second problem is what I mentioned before, that the prover can apply a different pi I to every query qi. And this is solved by a simple information theoretic compiler. This was done in BCIOP and also implicitly in this Genaratal work, where you can take a linear PCP in a weaker model that allows the prover to take a different linear combination for each query and compile it by adding one additional query, which just does a natural consistency check. So the additional query of the verifier just takes a random secret linear combination of the original queries and checks that the prover's answer is what is expected. So this is an information theoretic compiler from a multi-prover version of linear PCPs to standard linear PCPs that has a small overhead. And this compiler, the starting point here is called a linear interactive proof. You can consider this as an interactive proof where the prover can, instead of the proof being fixed and now the verifier being able to shoot at it linear queries, now you can think of the verifier's message as being a fixed vector, and the prover can compute any linear function on this vector. So this is kind of the standard model of interactive proofs, where provers, both honest and malicious, can compute any linear function of the verifier's messages. So we have an information theoretic compiler from a linear PCP to a leap. A leap has to resist these more adversarial attacks that can apply different linear combinations to the prover. Okay, so this is what I just mentioned. Finally, the third problem is that, as described, this proof system, this compiler only yields proofs that can be verified by a single verifier, the one who generated these encrypted queries, right? Because you need to decrypt. To decide whether to accept or reject, you need to decrypt the encrypted answers, and this can only be done by the verifier who holds a secret decryption key. Okay, and this is a serious issue. For instance, if you instantiate this approach using lattices, we still don't have efficient ways of getting around it. Okay, so how do we get around it? Well, the first way is just, look for designated verifiers around you, which means that some applications are meaningful even when you have a designated verifier, right? If I want to authenticate myself to a server, or there is some business partner I'm working with many times, why not have this one-time setup where the verifier has this secret key, generates this public information, and now I can prove to the same verifier very efficiently. And again, for lattice-based crypto systems, we have using this template, using linear PCPs, and this crypto compiler I described. We can have, these are the most succinct lattice-based proof systems. They only apply to the designated verifier setting. And for many applications, this is enough. Unfortunately, for most blockchain applications, it's not enough. The key point that was first made by Groth in EduCrypt 2000 is that if we apply the same template except for making the following two changes. At the PCP level, we add the syntactic requirement that the decision predicate of the verifier, the function that the verifier computes on the answers to decide whether to accept or reject, it has algebraic degree 2. So the previous Hadamard PCP I described, it has algebraic degree 2. It checks that the first answer is equal to the square, the second answer is equal to the square of the first answer, and that the third answer is equal to some constant that he knows, the linear combination of the right-hand side of the equations. Okay, so this is also the case for the GGPR linear PCP. Okay, so this requirement enables us to use an encryption scheme that works with bilinear maps. And bilinear maps have the property that you can encrypt information and you can check for any degree 2 polynomial of the information you encrypt, you can check whether it holds. That's a slightly simplified version. You need to have some entropic requirement and so on, but essentially bilinear maps give you a way to compile, so bilinear groups or bilinear maps together with some extractability assumption that you need to make. It's quite tricky to formalize, but using either bilinear groups with these types of assumptions or in the generic bilinear group model unconditionally, you can compile any linear PCP that has a quadratic verifier, quadratic in terms of degree, not computation time, into a publicly verifiable snark. Okay, and really the most succinct PCPs, the most succinct snarks that are being used in Zcash and in applications that Ishai will talk about are based on this approach. So they combine a type of linear PCPs with quadratic verification with pairing-based encryption scheme or bilinear groups. Okay, so I want to mention that there is a very different way to compile. So if you look at these, these are very practical systems. They're based, again, on linear PCP with degree 2 decision and by special type of bilinear groups, and these are very succinct. The downside is that the prover computation is very heavy in the sense that it needs to do expensive public key operations for every, there are two sources of inefficiency. On the information theoretic part, you have to do FFTs. So this is quasi-linear, so it can get very expensive if the circuit is big. Quasi-linear sounds good, but for big circuits, it doesn't scale very well. Also, memory is problematic. And the second problem is, on top of the information theoretic part, you need to do these computations in the exponent for every gate in the circuit. So there are two sources of overhead here. Again, for many practical applications, this is enough, but it doesn't scale in terms of prover computation. This is really the bottleneck for such systems. So a very different compiler in a recent works from crypto and previously from CCS, we have a compiler that uses this OLE primitive that I believe that Manoj mentioned or Kermit mentioned. So OLE is an arithmetic generalization of OT. So Kermit holds a pair of field elements, A and B. I hold a field element X, and I learn AX plus B and nothing else. Okay, this is the functionality of OLE. So we have very efficient ways of, or at least a vector version of OLE. We have different approaches, both lattice-based. This is a kind of a recent thing that is very good at generating vector version of OLE, which is good enough for this application. We have very good ways of, in terms of computation for generating these OLEs. And then we have this compiler that uses just a constant number of OLEs and a constant computational overhead to compile it into a non-interactive zero knowledge. So it's very good in terms of prover computation. It can actually work with constant computational overhead on the prover side for arithmetic circuits, not for Boolean circuits, arithmetic circuits over a big field. The downside is that they're not succinct at all. But if you have a fast network, And again, and there is systems like Ligero that give you an intermediate option where the prover is lightweight, it's heavier than this, but still much better. So if you look at three extremes, you have, if communication is very expensive, you have these super succinct things based on bilinear maps. You also have an IOP-based systems that I described before that are less succinct, maybe 100,000 bits. The bilinear group-based ones can be 1,000 bits. The IOP-based ones with symmetric crypto, something like 100,000 bits. These ones are very long depending on your circuit, but computation is the cheapest. And Ligero is some intermediate sweet spot where communication is square root, but prover is still somewhat cheap. So it's basically FFTs, but you don't have the public key crypto overhead for Ligero, right? And and IOPs are kind of similar, slightly heavier on the computation side and are better in communication. So this kind of shows you different trade-offs you can get by using different kinds. Here, it's just a different crypto compiler. The underlying linear PCP is the same, except that here you don't need quadratic verification. Okay, so this is the bottom line result. To get good computational efficiency, we use learning parity with noise. So it's a kind of a type of constructions that I or Alet will talk about next week in the MPC workshop. Okay, if you combine the two relaxations, so I have 5 minutes, right? Yeah. Yeah, so if we combine the two relaxations of allowing richer linear queries and interaction, we get the notion, the most liberal basic notion of linear IOP. So here you can have multiple rounds of linear queries. You can capture interactive proof systems such as the GKR and RR, right? Goldwasser, Kalai, Rothblum, and RR already mentioned. You can cast them as interactive proofs where in the end, the verifier makes a linear query to some proof. So you can really view them as a special case of interactive linear PCPs. Even though usually they're not cast as proof systems for NP, they're usually described as proof systems for polynomial time languages. In the case of NP statements, you have this long proof, but the verifier only needs a single inner product. For polytime statements, you don't need the long proof. You can have all the communication short. Here the communication is big, but you have this linear query by the verifier. And you can compile them, so now, okay, you have this alternative version which relates to this linear IOP in the same way that the LEAP model relates to linear PCP. So it's a model that allows the prover to compute a different linear function on every query. This is the ILC model of Bootle et al. Okay, it's a version. You can compile interactive linear IOPs into ILCs. And in terms of the crypto compilers, now there is a lot of work on a special type of linear IOPs in which the proof pi is not just an arbitrary vector of coefficients, but it actually corresponds to univariate or multivariate polynomial. So you can think of restriction of this model where the prover cannot choose an arbitrary pi, a malicious prover cannot choose an arbitrary pi, but rather pi, which is a low-degree polynomial. Corresponds to evaluations of a low-degree polynomial. Okay, finally, I want to present a recent kind of application of linear PCPs, which apply to a distributed setting. So here, the statement, normally we think of the statement, the theorem that you want to prove as being public. Here the theorem, the statement X can be split between multiple verifiers. So you can think of a secret sharing of the statement. You can think of just each verifier has a part of the statement. Say, I want to prove that I have a good financial history, so some of my financial information is held by one bank, another piece by another bank. Or you can think of encryption or commitment to the statement. So the statement is not available to a single verifier, yet we still want to enable efficient verification in this setting. And it turns out that if you modify the notion of linear proof systems into what we call a fully linear proof systems that apply linear queries, so it's a more restrictive model. In the standard linear PCP, the verifier can fully read X and then make a linear query, a small number of linear queries to pi. Here, the linear queries are made jointly to the concatenation of X and pi. X and pi. And these further restrictions make this notion meaningful or non-trivial to satisfy even for functions that are simple, polynomial time, or even finite. It makes the problem meaningful even in a pure information theoretic setting. So there is no trivial alternative of the prover, like traditional notions of PCPs or even linear PCPs are trivial to satisfy as P is equal to NP. This notion is not. And we also want a strong zero knowledge in the sense that if we only have limited access to X, let's require that X remain hidden. So as a result of these joint linear queries, X remains hidden. Standard linear PCPs, like the ones I mentioned, Hadamard and GGPR, they're fully linear, but the proofs are long. They're longer than the circuit. This is in a sense inherent. But it turns out that if you look at simple but still very useful languages, you can get fully linear PCPs that are very short, say are logarithmic in the length of the statement, or the circuit. And this was developed in a joint work with Bonnet, Boyle, Corrigan, Gibbs, and Gilboa, and Niv Gilboa will talk about it next week in the MPC workshop. So the main application is compiling honest majority MPC protocols that are secure against a passive adversary into ones that are secure against an active adversary. So this is, you can think of it as a distributed version of the GMW compiler, which is very efficient in communication. And I should note that also in the distributed computing community, a notion of proofs with distributed verifiers has been studied, and there is a very nice recent work by Naor et al. And Naor, Parter, and Yogev that shows application of machinery that was also used in the context of interactive proofs in the distributed context. There the focus is where you have interaction over graphs. You want to say if the graph is connected. Okay, I'm running out of time. I should just point you, if you want some written version of what I talked about, this modular approach, this is section 2 of the ePrint version of this paper. So if you want to see all the references, you can find it there. And I should say, I should conclude that I advocated this modular approach of separating information theoretic proof system from a cryptographic compiler. We have 4 different types, main types, many subtypes of information theoretic proof system, depending on the type of queries and whether we allow interaction. Most of the efficient protocols from the literature can be broken into these 2 components. And there is some work by Rothblum and Vadhan showing that in some sense this is inherent to black box constructions. So if your construction has a proof that in some sense is black box, you can extract some PCP out of it. But we do have some examples, in particular bootstrapping approaches, they kind of deviate from this paradigm. And there is a lot of room, many open questions and lots of room for progress that I can tell you offline because I'm running out of time. So thank you.